Welcome to Scene 1, Introduction to Geometric Brownian Motion. As the title appears at the top of your screen, note how this concept stands at the heart of many models in finance and physics. Geometric Brownian motion, or GBM, is a continuous time stochastic process. This means that it describes systems that evolve continuously over time, influenced by both predictable trends and random fluctuations. Let's break down its key components. Now, observe the stock chart emerging in the bottom right of your screen. Notice how the line, with its minor random fluctuations, mirrors how stock prices might move over a trading day. This visualization bridges abstract stochastic processes with tangible market behavior. Welcome to Scene 2, Brownian Motion Basics. In this part, we'll explore the core idea behind the random, yet continuous motion that underpins many models in finance and physics. Notice the title appears clearly at the top, setting the stage for our exploration of randomness in continuous time. Now, let's focus on the dot at the origin. Watch as it takes small, seemingly unpredictable steps. This is a visual representation of a Brownian motion. The dot moves in a continuous yet random manner, capturing the essence of stochastic behavior. Notice the trail left behind. Each short line segment marks a step in this continuous path. Building on this, we now connect Brownian motion to geometric Brownian motion. Here, the formula S of t equals S naught times the exponential of mu minus sigma squared over 2t plus sigma w of t succinctly captures how the exponential of a Brownian path gives rise to GBM. The circumscription you see briefly emphasizes this transformation. Now, we advance to Scene 3, Mathematical Formulation. Building on our earlier introduction to Brownian motion, let's focus on the core representation of geometric Brownian motion. Imagine a chalkboard where every stroke carries meaning. Here, notice the clean, uncluttered space designed to make our mathematical journey as clear as possible. At the heart of GBM lies the stochastic differential equation, ds equals mu s dt plus sigma s dw. In this formula, S represents our underlying process, mu is the drift, or the average tendency of the process, and sigma describes the volatility, which measures the randomness inherent in the process. Take a moment to let these components sink in. To clarify, on the left, we highlight mu. The drift, think of it as the engine that steadily propels the process forward. On the right, we see sigma, the volatility. This parameter captures the wild, unpredictable fluctuations, much like turbulent winds. By identifying these key elements, you can better grasp how GBM models real-world dynamics. Here, we take a significant step, the logarithmic transformation of our original equation. Notice how the equation now reads, d ln s equals mu a half sigma 2 dt plus sigma dw. This transformation is not just algebraic, it provides a clearer perspective, showing that the logarithm of s follows a Brownian motion with an adjusted drift. The deduction of the term a half sigma 2 from mu plays an essential role in this adjustment. This derivation is fundamental. It bridges the gap between the multiplicative nature of errors in S and the additive properties in its logarithm. Building on our theoretical introduction, in Scene 4, we now move to a dynamic simulation that visually represents geometric Brownian motion. Here, we begin by setting up our simulation space, a clear coordinate system represented by our graph. Notice how the axes are drawn right in the center, providing a structured stage for the experiment. To the top right, you can see our parameter legend. This reminder, mu equals 0.05 and sigma equals 0.2, directly correlates with the sample paths you are about to see. Next, let's watch as multiple trajectories of the GBM unfold. Each colored line represents a possible evolution of the process, influenced by both drift and volatility. Observe how each path, drawn sequentially, starts from the same initial value yet diverges in different ways. Notice, as we slightly adjust one trajectory, almost as if nudging the parameters, the path shifts subtly. This highlights the inherent randomness and sensitivity of the process. In summary, this simulation illustrates how randomness and fluctuating parameters drive the evolution of GBM over time. The careful design of our simulation space ensures that every element, from the axes to the legends, works in concert to deepen your understanding of these stochastic processes. Welcome to Scene 5, Applications and Summary. Building on what we discussed earlier, let's now consolidate our understanding of geometric Brownian motion by reviewing its core properties and exploring a real-world application. First, recall that GBM's logarithmic representation simplifies handling of multiplicative noise, a key tool in financial modeling. Next, consider its application in option pricing simulation and risk management. Finally, note its predictive power contrasted with inherent randomness. On the right, we visualize a simulation of an option pricing scenario. Notice how the graph, derived from a GBM function, evolves over time. Watch as a dot follows the curve. This represents the dynamic evolution of an option's price in a real market. By highlighting the option pricing simulation, we make a clear connection between theory and practical application. Observe the link between the bullet point and the animated simulation.